In this video, we're going to consider a physics question involving the rates of change that we just distinguished between. So in the previous video, we talked about average rates of change and instantaneous rate of change. Average rate of change is when you've got a starting point and an ending point, and you want to find on average what was the rate of change of whatever your function is outputting over that interval. An instantaneous rate of change is when you just have a single point and you want to find the rate of change of the function at one point. So here we've got a pretty standard physics question. Balls being tossed in the air or off tops of buildings. So here a ball is tossed upward off the top of a building. So you're standing on the top of a building and you throw the ball and it goes up and then of course comes down and eventually will hit the ground. We have a function, thanks to Galileo, I believe, that models the height, which we'll call h, in feet of the ball above the ground after t seconds of being tossed. So just a little bit of, insight into what this function, how it's built. You don't really need to know this, but, this function here that gives us height on the left for any time that you want to put in. It's not random. Each number here is very specific. It's actually really cool how it's built. So the function we have here is negative 16t squared plus 48t plus 64. So each of these numbers, again, have a particular meaning. So this is just a little bit of insight into this. So the 64, this is the initial height. So this is the height of the building, basically. If you're standing on a building at time equals 0, plug in 0 for t, you get 64. The ball is 64 feet above the ground. So basically how tall the building is in this case. Then the 48 in front of the t term, this is actually the initial velocity of the ball. So it is a positive velocity, that means going upward. A negative velocity would mean going downward, losing height. The height is decreasing if the rate of change is negative. So this means that initially, whoever you toss the ball up from the top of the building with this amount of force or this amount of velocity behind the ball. So 48 feet per second would be the initial velocity. Then the negative 16 t squared, just the negative 16 in front of the t squared. This is a constant that represents acceleration due to gravity. Sort of. It's half of the acceleration due to gravity, but when it's a little more complicated to get into that at the moment. So that negative 16 comes from the gravity constant of negative 32 feet per second squared, which would be the acceleration. So I don't know if you are all taking physics or if you maybe have already, or if you are now, or if you will. You'll learn about each of these things. Again, this is just a little bit of insight into this function. So we're going to find a few different things. The first is the average velocity of the ball for the first 3 seconds. The second is the velocity of the ball at 3 seconds. The third is the average velocity of the ball for the whole time it's in the air. And the fourth is the velocity with which the ball strikes the ground. So please pause this video and see if you can kind of figure out which kind of rates of change is each one of these parts asking about. So basically, is it average rate of change or is it instantaneous rate of change? For each part, pause this and write down what you think. So the average rate of change is normally pretty easy to spot out because in the question, it will say average. So in part A, we've got average velocity. Okay. So we're going to be finding in part A the average rate of change. And remember, we have a neat little acronym for that. So this is the average rate of change. And it's for the first 3 seconds. So that might sound like it goes from 1 to 3 seconds, but we always start the time at 0 when in these kinds of situations. So the first second would really be from 0 to 1. The second second would be from like t equals 1 to t equals 2. And the third second would be from t equals 2 to t equals 3. So the first 3 seconds is really going to be from t equals 0 to t equals 3. I just think about if you started a timer, right? The first minute or per second would be when it hits 1, but you'd start it and it would start right at 0, right? So with average rate of change, we always need an interval. So this is going to be from 0 to 3 for part A. For part B, we just want the velocity at 3 seconds, right? That's 1 point in time. So that's an indicator that you're finding instantaneous rates of change, is when you've only got 1 point. So this would be an IROC, instantaneous rate of change. This is going to be at t equals 3. T equals 3 seconds. Part C, we want the average velocity of the ball. Okay, so again, that's average velocity. So we basically have 2 things happening, average and just velocity. So the average velocity, in this case for the time it's in the air, okay, so that's starting at 0. And we don't actually know how long it's in the air for. We might have to figure that out, so we'll just put a question mark here. And then lastly is the velocity with which the ball strikes the ground. Okay, so it's striking the ground is at an instant in time, just 1 point in time, right? So this will be instantaneous rate of change. Again, we don't know when the ball strikes the ground, so I don't know the time yet. We'll probably have to figure that out. All right, so for part A, we are, again, finding average rate of change. So we're going to look at the average rate of change from the interval 0 to 3. Now, I know it's average velocity, but remember, velocity is change in distance over change in time. So when we find average velocity, in this case, our distance is measuring height. So it's going to be change in height over change in time. No derivatives involved for average rate of change. Okay, so again, velocity, change in distance over change in time. So we just want the change in the height over the change in time. So this is going to be h of 3, the height at the end, minus h of 0, the height at the beginning. Right, remember, look back in your notes, it's f of b minus f of a. So b is the ending, a is the beginning. Here we just have h for our function instead of f, that's okay. Okay, then it's over the change in time. So that'll be the ending, which is 3 seconds, and the beginning, which is 0 seconds. Okay, so let's figure out what this is. So in the first part of the numerator, we have h of 3, so we're just going to plug a 3 into the height function. Negative 16 times 3 squared plus 48 times 3 plus 64. Then we're going to plug in 0 into the height function to find h of 0. So we'll subtract h of 0. So that's negative 16, 0 squared plus 48 times 0 plus 64. And that's all divided by 3. 3 minus 0. So you might need to grab your calculator and figure out what each of these things are, and that's okay. Make sure that you're comfortable plugging these kind of numbers into your calculator. So figure out what this chunk is first, and then this chunk separately would be my suggestion, and then subtract them. So when you plug in the 3 into the height function, I think you will find you'll get 64. And when you plug in a 0 into the height function, you'll get 64. And of course, it's all divided by 3. 64 minus 64 is 0. And 0 over any number, as long as the denominator isn't 0, is just 0. Okay. Rates of change always have units associated with them. Here in the numerator, this was distance or height. That is measured in feet. And then in the denominator, this is time, that's measured in seconds. So 0 feet per second is the average velocity of the ball for the first 3 seconds. Now, if you're wondering how, like, what? Like, how does that make any sense? Here is what that means. So if we just draw a really kind of simple picture, where maybe here's the building, and we draw in the trajectory of the ball. So maybe, you know, here's the ball, and then it gets thrown up, and then it comes down, right? So it might look something like this. So it starts at 64, a height of 64. So right here at this point, this is t equals 0, and the height is 64. Then what we found is that the height at 3 seconds, right from here, is also 64. So the ball went up, and then it came down, and then according to our equation, the height at 3 seconds is actually the same height as when it started. Okay, now that's okay, right? That makes sense. So where does the 0 come from? Well, on average, if you only knew the starting and the ending, and you didn't know what happened in between, that it went up and came down, on average, it didn't go anywhere. It went up for the same amount that it came down. And so on average, it moved 0 feet per second in this 3 seconds. Another way to think about this is if you were to sketch in the secant line, which is a graphical interpretation of the average rate of change, right? The slope here would be 0, it's horizontal. So now it should make a little bit of sense. Okay, for part B, we've got just the velocity of the ball at 3 seconds. So this is instantaneous velocity. So this is the instantaneous rate of change. So this is going to be the derivative of h, so h prime, and we want it at 3 seconds. So this will be h prime of 3. We just want how fast is the ball going after 3 seconds from being tossed. Okay, so we need to find the derivative of h. So let's say h prime of t. Where's our function up here? So it is -16 t squared. Okay, so when we differentiate that, this is simple power rule with a constant multiple in the front. So the 2 is going to come down and multiply by the -16. Or if you want to write it out a little more carefully, we'd have -16 times the derivative of t squared, which is 2t. Right, we subtract 1 from the power, and we'll get t to the first, so 2t to the first. Then sum and difference rule, we add the derivative of 48t. 48 is another constant multiple. The derivative of t to the first is just 1. Then we add the derivative of 64, and that's a constant all by itself, so its derivative is 0. And if we just simplify this, we end up seeing that our derivative of the height function is -32t plus 48. Okay, so now we just want to plug this into, plug 3 right into our derivative equation. All right, so we're going to plug a 3 in for t. We've got -32 times 3 plus 48. When you calculate that out, you will get -48. Again, this is a change in height over time. Even though it's instantaneous, it has the same units as the units of the output, which is feet, divided by the units of the input, which is time, which is seconds. Okay, so this will be feet per second. Okay, so why is this negative, and does that make sense? Well, if we draw a picture again, just a really simple picture. Here again is the building, 48 feet tall. We've got this ball, right, being tossed up, coming down, something like that. And we already found out that t equals 3 seconds is right here. Well, what's happening is the ball is actually, it's going up, and then right here, it's on its way down. So the trajectory of the ball, right, is heading downward. That's what the negative means. Okay, velocity has a direction. So if it's negative, that means the height is decreasing. So in this case, going down. You could have it going left or right or forward and backward. But in this situation, the negative means the ball is going down. The 48 means that in the 3rd second, so if you look at just this snapshot 1 more second in time, from 3 seconds to 4 seconds, so in the 3rd second, the ball falls approximately 48 feet. So the derivative, or the instantaneous rate of change of anything, is a way to approximate a rate of change in just if you increase your input by 1. So in the 3rd second, the ball will fall approximately 48 feet. It's not exact, it's just an estimation. So you can see that at different times, right, the instantaneous velocity is going to be different, right? It'll be positive until we get to about here, because the height is increasing. Then at every other second from here on down, the velocity should be negative, instantaneous velocity, because it's going downward the whole time. And it should probably increase in its absolute value, because the ball should be going faster the closer it gets to the ground. So let's see, for part C, we've got the average velocity of the ball for the time it is in the air. Okay, so again, we're looking at average rate of change. We know that the time when the ball starts to be in the air is 0, but we don't know when the ball hits the ground. So in other words, we don't know this time, right? We want basically the average rate of change between the beginning and the ending. So let's kind of make a new sketch here. So, right, we're looking for average rate of change from 0 to the ending point. Let's call this, let's call this T final, right, when the ball hits the ground. So we're going to need to find this. We need to figure out what this is. So if we draw a little picture again, I love pictures. I think they're super helpful. It's the same picture though. Let's be consistent and draw it the same way. So here we've got our building. Again, here's the ball start. Here's the ball end. Here's t equals 0. Here's t final, which we don't know what it is. But we do know that at the beginning, the height is 64. And we do know that at the end, we actually know the height. The height of the ball above the ground, when it's on the ground, is 0, right? It's 0 feet above the ground when it's right on the ground. So this piece of information here is really crucial to actually figuring this out. Okay, so we know the height is 0 there. We can actually find the time that it will take to hit the ground just based on that information. So how do we do that? Right, we need the ending time here. So what we're going to do is set h of t, or h, equal to 0, and solve for time. Right, this will give us the time when the ball will hit the ground. Okay, so our height function is -16 t squared plus 48t plus 64. So we're just going to set that whole thing equal to 0. Okay, we know the height is 0 and we're going to find the time. You could go ahead and use the quadratic formula on this. I would suggest just trying to factor first. So if we took out a -16 from everything, we'll be left with t squared If we divide 48 by negative 16, we get negative 3. And if we divide positive 64 by negative 16, we get negative 4. I think that this is factorable because we have two numbers that will multiply to negative 4 and add up to negative 3. All right, those will be t minus 4 and t plus 1. Okay, now remember the reason to factor something when you have 0 on one side is that if you have a product of things that multiply to give you 0, one of the things has to be 0. So we've got negative 16. That's never equal to 0. We've got t minus 4. That equals 0 when t equals positive 4. Then we've got t plus 1. That equals 0 when t equals negative 1. Now, based on our situation, t equaling negative 1 doesn't make sense, right? That would be before the ball is tossed. That's just not something that makes sense in this situation. So our answer here, the one that we're kind of going to use, is the t equals 4 seconds. So this is t final. So in other words, we can kind of erase this fact that we don't know. Well, we'll leave it there. We'll say, so this is 4 seconds. Right, this is actually 4. So what we need to do now is find the average rate of change from 0 to 4. So this will be h of 4 minus h of 0 over 4 minus 0. Okay, h of 4, well, if you plug a 4 in, I mean, you can do it, but we found that the height is 0 when t equals 4. And, you know, here too, the ball's on the ground when t equals 4 seconds. So this should be 0. The initial height is that we found before, it was 64. 4 minus 0 is 4. When you divide negative 64 by 4, you get negative 16 feet per second. Okay, so this is on average. Again, remember, it's like the slope of the secant line if you were to kind of graph this function. Now, this isn't a graph of the function, it's more of a model, just kind of a picture to help us. So on average, the ball fell every second over those 4 seconds, 16 feet. But of course it went up and then came down, but on average, the ball went 16 feet downward per second in those 4 seconds. Okay, so that's how we interpret this. So on average, the ball fell, because it's downward, 16 feet each second while it was in the air. Now we know that, again, the velocity was different instantaneously, right? We actually found in part B that at 3 seconds, it was falling at negative 48 feet per second. So this is just an average, right? Sometimes it's got positive velocity when it's going up. Sometimes it's got negative velocity. And so on average, it lost 16 feet per second. Okay, our very last part in this question is the part D, the velocity with which the ball strikes the ground. Okay, now this is instantaneous velocity or instantaneous rate of change. And part C is actually it's done the hard part for us for this question because we figured out when the ball hit the ground. So we don't need to do that again. All we need to do here is plug in t equals 4 into the derivative. Okay, so we want the instantaneous rate of change when the time is 4 seconds. Okay, so the derivative we found already, I believe that was negative 32t plus 48. So we're just going to plug in a 4 into here. Negative 32 times 4 plus 48, that comes out to be negative 80 feet per second. So that should make sense, probably. I mean, it's going faster than it was at 3 seconds, right? We found that in part B, it was going negative 48 feet per second. Still going downward though, because the velocity is negative. But, that makes sense with our experience that it's going faster the longer that it has fallen. So right when it hits the ground, I know it's stopped at that point, but it's, I guess you could see like really right before it hits the ground, it's going at a speed of 80 or has a velocity of negative 80 feet per second. So the next video, we will look at this kind of average rate of change, instantaneous rate of change in the context of economics.